Welcome back. Another poor audio quality video on angular momentum. Gonna get some subscribers from this one. Gonna take a look at some questions from these angular momentum problems that I've got posted. And I created these problems quite a long time ago. Keep reusing them here and there, but this problem 7 and 8 are both pretty comprehensive questions for conservation of angular momentum for systems that don't have any sort of linear motion with them as well. And this first one, take a look at the setup. I'm not going to do all the calculations. I got the numerical answers on the side. So if we take a look at the setup, this will be to help you get the problem started. It says we got a scrawny dude in a spinny chair, and it's holding 10 kilogram mass in each hand at arm's length, 0.65 meters from the center of mass. The masses are much heavier than his arms, and passerby are intrigued by his apparent strength. So evident scrawny dude, zoom in here, the arms of scrawny dude are extremely small because he's scrawny. But so we can ignore the mass of the arms. We can treat those as thin, rigid rods. And the masses at the end we can think of as point masses. So a simplified picture from an aerial view would look like what I've got right here, where you've got a 50 kilogram mass for the person's body, pretty much around the center, and then two 10 kilogram masses in the hands. It says mass 50 kilograms, and for physics' sake, approximated as a cylinder of radius 0.3. He's scrawny, remember? So 30 centimeters across. And another dude sets the first dude into motion at 3 radians per second. That's the initial omega. So we want to know the angular momentum of the scrawny dude at 3 radians per second. And then if the scrawny dude were to pull in his arms 0.3 meters from the axis of rotation, what will be the new angular speed? So they were 0.65. Go ahead and note that on this simplified version of the picture. That's 0.65 on both sides. And then at this point, from the center of the person to where the mass is going to be 0.3 meters, because that's the radius of this scrawny dude's torso or whatever is going on. I don't know. Silly problem. But for the setup, if we want to calculate what the angular momentum is for the scrawny dude, then we have to take the I value for the scrawny dude and multiply it by the omega. And in this case, the scrawny dude's angular momentum, we're going to include the masses. So this is going to be the total rotational inertia. So for the scrawny dude, it says we can treat him as a solid cylinder of radius 0.3. So solid cylinder would be 1/2 m times r squared. So we'll put mass of the dude and the radius of the dude. And then we got to add in 2 times the mass of the 10 kilograms. So that would be the mass of the mass, I don't know what else to call these things, multiplied by their radius from the pivot point, which is the center of rotation about the scrawny dude. So radius of mass squared, all multiplied by that initial omega. So that's how we could set up what the total rotational inertia is. Now these two values, MD, we know what that is. It's for the dude, it's 50 kilograms, and the radius of the dude is 0.3, and then we got the mass and the radius for where the masses are. So each of those would be 10 kilograms. So we calculate that up, you should get 32.1 kilogram meters squared per second. For part B though, it says if he pulls the masses in to his body from 0.3 meters from the axis of rotation, sorry, I'm having trouble reading my own words, what will be the new angular speed? So in this case, it's going to be a non-collision conservation of momentum problem. So we're going to have this total angular momentum initially equaling a total angular momentum final, but none of the masses changed. It's just going to be the radius. And in this case, everything we have up here goes in for LTI, total rotational inertia of the scrawny dude and the masses at arm's length multiplied by omega. And then we're going to have the same sort of setup, but we're going to have to modify what the new radius is. If we go ahead and do that setup and maybe even put in a couple numbers here, we'd have 1/2 Oh geez, I'm using the wrong marker there. That marker's chubby marker. So we'd have 1/2 times, 50 kilograms multiplied by the radius of 0.3 for the scrawny dude's torso squared, plus 2 times the 10 kilograms multiplied by 0.65 squared, and all that is going to be multiplied by 3. And then for the final side, we're going to repeat some of that. We're still going to have 1/2 times 50 times 0.3, but now the two 10 kilogram masses are going to also be a 0.3. And that's going to be multiplied by an omega f. So the only thing we're changing is from 0.65 to 0.3 meters for where the masses are. And if we treat this as a non-collision conservation of momentum problem, that's all it is. We just got to change what the R value is and we're good to go. And if you do that, you should be able to get a new angular speed of almost 8. He's booking it. Taking all that mass that was far out and bringing it to, well, geez, I mean, you bring it into about half of the radius, and that getting squared to give you 1/4 of the rotational inertia, and so you should be cranking. Okay, so that's the setup for number 7. Let's take a look at the setup for number 8. Remember the game show Wipeout? Of course, everybody does. There was a game in Wipeout where someone had to stand on a pedestal and a big sledgehammer-looking thing is swinging around. They had to try to jump over it and not get knocked off. So this poor game show contestant, they just can't do it. They're going to get hit. So during this game show, the sledgehammer thingy, abbreviated SHT, is swung around horizontally at contestants. Assume that everything's frictionless and we don't need to worry about air resistance or anything like that. The sledgehammer thingy is a rod of mass 200 kilograms and length 8 meters, rotating about its endpoint, and as a 75 kilogram extra weight and foam added to the end. So that'll be treated as a point mass. And the sledgehammer thing is swinging around at pi/4 radians per second. What a convenient number. And the contestant has a mass of 80. So what is the angular momentum of the sledgehammer thing before impact with the contestant? So we'd want L for the SHT, and that's going to be the I value for the SHT multiplied by there's a lot of SHTs there. We even have an I in there. What do you know? So if we add that up, we should have the I for the rod plus the I for the, what do we call that, the extra weight, put that as IW, multiplied by the omega for the whole system. And since it's a rod rotating about its end, we would say that it has 1/3, call that mass of the rod, times its length squared, plus, let's say for the weight, it would just be the mass of the weight times its radius squared, which would be the length of the rod, multiplied by omega. So that would be our setup for the angular momentum of the sledgehammer thingy before it makes contact with the contestant. And if you calculate that out, you should get over 7,000. What about part B? The SHT hits the guy inelastically. So it's going to be they're going to stick together, and the guy holds on to the SHT. He's got 2 arms full of SHT. What will be the new angular speed? So it's going to be kind of like what we're doing here, except now it's a 2-particle system. It's not going to be just one thing gaining or losing radius value. For part B here, we're going to have the SHT plus the guy, I'll just put it as a G initially, is going to be equal to the 2 of them together. It's going to be the I total multiplied by some new final omega. And since the guy wasn't moving in the beginning, that's just going to be equal to 0. So we can put that whole expression that we've got, 1/3 m rod times L squared plus mass of the weight times L squared, all times the initial omega, which in this case was pi/4 radians per second squared, will be equal to, let's see here, it's going to be the same thing, but now it's going to have the guy added in. So same thing. Do I want to write it all over again? I don't think I do. I think I'm just going to do this Copy. How do I paste it now? That's a good question. I'm not having a good day here. This was a mistake. Paste? Hey, what do you know? So we'll take that. I could have rewritten in that time. Plus, and we'll treat the contestant as a point mass, so the mass of the guy, and he's at the length radius squared, and all that will be times an omega f. So in this case, it's two objects, but it's really just modifying by adding in what the rotational inertia of the guy is. Anyways, that's some setup for that in case you need some help with it. Hopefully it is helpful. If not, sorry you had to watch all this, but at least it was interesting. Maybe, hopefully. Anyways, have a good day.